Hi guys, today my guest is Manuel Ramsaier, and I'm absolutely certain I butchered his name. and I've got many questions over the years about topology optimization, which is to some degree connected with FEA. And since I know next to nothing about it, I figured out that I will find a guy who does. So Manuel finished his PhD in the field. So I guess that I will ask him a lot of difficult questions as we go on. But firstly, Manuel, I think that it would be good if you tell us a bit about yourself and where we can find you online as well, because I know that you have a YouTube channel that has like few hundred more subscribers than I do.
Ooh, okay. Yeah, sure. No worries. Yeah, I'm Manuel. I have a YouTube channel about engineering that started quite a while ago, I think 2014. And I studied mechanical engineering. I'm from Germany. And the way I went to the field of topology optimization was during my studies. We have this sort of practical semester. You guys have something like that also where you go?
No, we don't. I've heard that you have that. I think that what we have in civil engineering is that you have to go for like summer work at the building site as a student to learn the ropes of being a civil engineer. So that would be kind of similar, but we don't have the semester. We just have like holiday thing that you have to complete in order to finish studies. So it's not precisely the same. And university doesn't help you with finding the job. But you know, since you're like basically a free labor, it's like everybody's happy to have you.
Yeah, sure. Pay less, get the workforce. Well, for the practical semester is somehow related or somehow the same. You also get one semester in a company where you should learn how it's done. And I've never heard anything about FEA until that point. This was my fifth semester. And I had to do something with topology optimization. So they sent me to courses, to Altair, and got a lot of things to learn.
Oh, wow.
And this was a great adventure, and it stuck with me since then.
Yeah, but I'm also super surprised that the way like they knew that you're like only a few months working there, and they still like invested in training you and so on. That's so cool.
But
I like this approach.
I really am grateful for that too. But you have to say they pay a lot less for students. So they paid for the training, which was 4 days training, I think 200 euros. And it would be 2,000, I think, for a normal engineer. So they got that knowledge and all the stuff you get.
Since we both worked at university, maybe there's a way I can still get the status of a student to train myself.
Yeah. Or you form some relation to them, so then you teach something. If you're teaching, then you also get the courses. But yeah,
that's so cool.
There's some different conditions. You also can have something called like a training flat rate. Large companies have them usually. That you can get to every training for free.
So you work in a big office and they
and this would be also possible. So they have different conditions. But this is the way I got to topology optimization, and I thought it such a cool tool because
would it be fair to say that it was by accident?
Yes, definitely. It was definitely.
This is how I got into FEA as well.
It was surprising. Well, you have maybe a little bit to get a little bit around that. I have always had my ways around dealing with programming, computers, stuff like that. So I'm not the typical engineer who goes into the garage and builds his stuff. That's not me. But what I'm good at is programming, software, something like this. So I was in the way of finding my way to that engineering field, what I want to do later on. And this is what struck with me, because I found it very cool. Yeah, so you can say, the structure fails or not. Yeah.
It's amazing how our stories are similar, because like I was learning how to code, and I still program in several languages. So that was like something that really got me started into FEA. It made it easier to access it. And since I'm not a sport guy, I play computer games my entire childhood. I have like an instinct to use software, I've seen so many different user interfaces in so many games that it's very hard to surprise me at this point. I just know where to click for stuff to happen.
Yes. Yeah, same goes with me.
So I know how you started, but to be honest, I'm still murky about topology optimization. I mean, I know that it makes those impossible organic
pictures.
Shapes that look weird to the eye. But if you could explain what it really is, and there is a follow-up question about what's the difference with structural optimization, because I'm a civil engineer, so we got taught how to do structural optimization, that the structure should be lightweight or maybe not so much welding and so on. So there are choices I'm doing day to day in my work that technically are optimization, but I'm pretty sure have nothing to do with topology side of the thing. So if you could explain that would be awesome.
Sure. So topology optimization is one kind of structural optimization. So I have actually in my Ph.D. defenses talk, I had some slides about this, which I could show you. Because it illustrates that kind of it.
Of course.
So let me see. This will be here. Switch over here. So, I'm sorry.
Oh, such a beautiful PhD defense presentation.
Well, it was originally in Germany, so it was in German, and I really automatically translated it with PowerPoint. So there is
it must be awesome.
There was certain some errors in here, but we will find it one way or the other. So this is structural optimization and different kinds of. So if I run through there, you have, for example, the choice of your construction. So you can make or build a bridge by different kind of principles. You have bridge like this, framework bridge like this. And you also can change the material. It's also kind of a structural optimization, because if you want to save weight, lighter material seems to be an obvious choice. And topology optimization is really one kind of these optimization. Topology changes the number and position of the structural elements. So if you see on this line here, that you have different elements, different number of elements, and also different number of forming holes. Because if you add some elements to it, you're changing also the number of holes, or you could also say the section cuts, and that's the topology of the structure. And this is by far the most free way how to change your shape, because you can only change the form. So that means in this case the positions of the nodes of the structure, and also just not the sizing, so the dimensions of the structures, but you can also change how many and where. So topology optimization includes both form and sizing to a certain degree.
Okay. Okay. So it's like from the point where you know which material you've selected and what type of construction you want to use, the rest is basically the domain of topology optimization. So if I ever change the way that my trusses are braced, does it mean that I did topology optimization before?
If you did exclude certain elements or did include some elements, that's topology optimization, because you are changing the topology in the goal of making the structure better. But so this is kind of a topology optimization.
This makes me so proud. PhD researchers are so smart. I did this not even realizing, but of course, I understand that the beauty of it lies in automating this stuff, right?
Yeah, and the thing is, well, we said that we changed the number and the positions, but how can we know where to put them? Because you see here three different variants. Those are normally not done by hand, but topology optimization, how it's used today, is using computer-graphic algorithms. So you define an objective, for example, the stiffness or the mass you want to maximize or minimize, and then you have some boundary conditions, and then you can see what your algorithmic structure will get you. So that's codes which are running.
Wow. And can you request, for instance, the lines that to be straight? Because like, topology
Well,
optimization
yeah,
to me looks like those crazy 3D printed shapes that look like intertwined branches of a
yeah,
tree, So
yeah.
that, to me, that's like, as a civil engineer, that's like, what a mess, basically, right? So I would be instantly interested in having like straight lines, straight
Yeah.
angles, and things like that.
Well, there are different ways of doing a topology optimization. The ones with the more bionic shape-looking results, those topology optimizations are mostly done with density-based methods. But if you want to have, for example, just straight lines, you could also give just straight lines from the beginning. Because I don't know if you ever saw that, but it's just like a lot of knots and linked one node with each other node with straight elements. And the topology optimization then finds out which elements to keep and which elements to just throw away. And then you get a fine set of straight bars. And by the fine size of the grid, you can, adjust the simulation.
Okay, so basically you could either have like a 3D shape that is like a solid brick, and then it would remove element after element, and the shape that remains would be like organic. But if you just have a lot of lines, what remains has to be straight lines, because this is what remained.
Yes, this is one possibility of doing a topology optimization. Well, there are so different manufacturing constraints and stuff like that. So you can also do that with a density-based approach. So this is also possible.
Yeah. How it is applied to real problems, because for better or worse, I instantly think about civil engineering, and I wonder, like, if I would ever do a design, would it even make sense to do like topology optimization of a building structure, right? I admit that I do pressure vessels more nowadays, so I don't even do buildings, but from that standpoint, like, would it even be worth an effort to have the domain and do this? Like, what are the main applications fields and where topology optimization is used the most? Because I get a feeling that it's not civil engineering, but maybe I'm wrong here.
Well, there are some concepts, and also I think bridges are also partially are designed with topology optimization in mind. It's often also used by architects, which just want to get some ideas. And then, now we get into the talk about how it's approached or how it's implemented into the real world. So the question is always, if you have topology optimization, can you kick off all your designers? Because basically you're giving a problem, and then some mathematical yada yada, and then you get a structure, and then you can build it or even print it, and you're done. Is that the case? No, it's not the case. You always have to do your interpretation and look at it from a critical point of perspective with engineering knowledge and stuff like that. And also, you cannot kick your designers. You have to reconstruct that.
You can fire some of them, I guess.
Well, I would not suggest that, but well, it's heading into this direction of having reconstruction methods, which always get you also a head-like geometry, but they have been trying that for decades, and it's still not there. So it's rather complicated. Yeah. And also,
is topology optimization so old? I was thinking that it's like a new thing.
No. That's no. It's really old. I think the first ones around the 70s, 80s. Well, it like started with the homogeneous method, where they introduced like a material which has holes in it, and adjust the alignment and parameters. And I think the sim method got introduced, I think, in the 80s. Something like that. I would have to look it up, but it's rather an old technique.
No, it's like I'm surprised that it took, like, because it's, I guess, like with nonlinear FEA. Technically, nonlinear FEA was around for like decades and decades now, right?
Sure.
But if you start doing nonlinear FEA in design, everybody thinks like, whoa, that's new. Like, it looks like something new. To me, topology optimization is exactly the same. Like, I haven't heard about 10 years ago, I wouldn't heard about topology optimization being used in practical cases anywhere. So like, since I'm not in a field, I didn't read the research, it seems like a very new thing, but perhaps that this is how things are adopted.
That's also correlated with the calculation power. So if you get more resources, then you can also
obviously, yes, absolutely. Yeah, I guess that's the same with FEA, right? So where would you use it like to be most efficient? Like that's the curious part, I
Okay,
guess.
so well, optimization is broadly speaking applicable everywhere where you want to optimize something. So it's really broad. But if you want to narrow it down, you could say that the structures which benefit the most from topology optimizations are the ones which you want to make as stiff as possible or as low weight as possible, because those are the two typical formulations you would do in the industry. So once is maximize the stiffness of a certain part with a certain volume which you have at disposal. And the other formulation is minimize the mass, but this stress constraint or this displacement constraint has to be fulfilled also with the optimized structure. So those are the two formulations which I use the most.
I agree. Like, well, obviously I agree because I have next to no knowledge about it. But what I'm curious about is what you described is basically what engineers in all fields strive to, right? If you would ask a silo designer what the goal is, that he would tell you that, you know, I want to have the most lightweight silo design possible, right? Yeah. And they do a lot of various tricks to achieve that. But I'm pretty certain nobody ever used topology optimization to design silos, and I think that there is a good reason for it. Like like the design is so complex that it just wouldn't work properly. Like the governing mathematics of topology would be crazy, most likely, especially since shell buckling is included, right? But I also haven't heard people doing like entire buildings, right? So I guess that there are fields where people like where topology is like industrially used as a standard, and I guess this is what I would like ask about. If
well, I don't have the numbers exactly, but I think that it's not that widely used yet. But it's used in part design the most, I guess. So, well, you could say that it makes most sense in those areas where you have a lot of bending stresses and you are free to change your design space so that you have just beams which have tensile and compression stresses. So if you have a load case like this, this would be perfect, because that's what topology optimization does. Because bending stress is suboptimal, and it wants to divide that off into tension and compression stresses.
Yeah, sure.
And for the silo, you have to contain your whatever. So you would have to have a certain amount of material on all the surface. You cannot change it to ribs. It's not possible. But I think for silo design, maybe topography optimization is more suitable. This is how you can form your sheet metals, make it more stiff just by changing the form.
Oh, okay. Yeah, that would be something. That would be something for sure. Okay, so there's a branch that does that. Okay, that's curious. So what do you do at your work then?
Well, my work is not that much correlated with topology optimization in the moment. So I'm working at an engineering bureau, and we are doing lots of different stuff. But the main focus is landing gears, and I'm also doing cranes. So for crane, I have to investigate also the performance, and that's where you're the expert, buckling stuff like that. This is more it, and less topology optimization. And for the landing gears, well, topology optimization is a thing, but I'm still fairly new to the company, I must say. I'm there since August, as I finished my Ph.D. last year in November, so it's pretty fresh. Still green behind the ears.
Sure, but. So which direction would you go in that case? Like, do you want to use topology optimization in general? Because, like, you know, we both have our PhD, so we have a rather strong feelings about how useful those things are. So,
well,
I guess my question is, do you see a future in the field for yourself?
Well, I can definitely see that. Topology optimization and its application in especially aircraft design. So if you talk about landing gears, all the levers and stuff like that,
Okay.
definitely a thing. And also, I very much like the way of optimizing. But I have to tell that the PhD thesis was not completely all just about topology optimization, but rather more or less the design process and how to integrate it and how to get your topology optimization result back into something which is useful. So I spent a lot of time coding and figuring stuff out how to get this optimization result back into something usable CAD format automatically. So this is more or less this route I went with. I can see a future in there as well. So coding will stick with me. I'm sure this will always be the case, but I'm not.
But then it's
a good thing.
Like, this is something people always ask me. Since you code in few languages, why don't you work in IT? They pay better, right?
Really? Yeah. I don't know that really, but I think you can look at it from another perspective. That there's still so much to do in engineering design, which the tools from IT you could use. So
yes,
I think that's a pretty big opportunity and something really I want to foster in the future.
Okay, so since we already doubled in IT, and it's funny how when engineers talk, it always ends in IT at some point or another. What software are available? Like, are there like commercial grade solvers that, because I assume that there is a solver involved, right? Could you buy one? Or is it like super PhD stuff? Like how this looks from the technical perspective of things?
So
software, let's say.
Yes and no. So there are lots of commercial solvers out there. I get the notion that every CAD software now includes some way of generative design, topology optimization. For example, I heard, I've not tested that, but I've heard that Creo 7 has it. And also Autodesk, Fusion 360. But topology optimization, so how I got introduced to the topic, and I think one of the first guys who ever done that, and also standing behind that the whole way is Altair. So Altair with Hyperworks and OptiStruct, this is pretty big. They're pretty big in optimization or optimization-driven design. That's their whole slogan, right? So they are pushing a commercial solver. So what they're using industry-wise is the SIMP method. And the SIMP method basically is as easy as 99 lines of MATLAB code, which you can download, look at it, and get it. But the devil is in the detail. So if you want to take the advanced filtering, implement your manufacturing constraints, overhang angle for 3D printing and stuff like that, minimum member size, maximum member size, stuff we could also go into, then you would end up most likely at a commercial solver. But as I said, OptiStruct is one, but Abacus has also some topology optimization tool and Ansys as well. So they are mostly included in the mainstream solvers nowadays.
Okay, so basically big FEA players have the topology optimization part of their work as well. I actually think that Nastran has something. I haven't heard a lot about it. I just like heard that if you do like TED 3D solid shapes, you could do something to them. In like, of course, like this is not what I do, so I didn't inquire about it too much, but it's funny, like the same companies does this, right?
Yeah, sure.
It's like
so
surprising. I was thinking that you will throw names I never heard about, and so far you listed companies I was aware of. And
well, like, maybe there are some names I don't know about, but for sure. So you also get for Reno. Reno is a CAD software, which is also more. There are generative plugins for that, and so you find it all there is. So if you have, because it's so easy to implement, if you have a finite element solver, the topology optimization code is not that big. Just need to get
Okay. So
function call of the
you
finite
can just
element.
add it on top of the FEA,
Sure.
FEA that you have already, right? And
Sure.
it uses linear FEA, right? So the constraint you can have is just like maximal stress, maximum deformation, and it will do like linear analysis and check, because otherwise it would take ages for it to compute, right?
For gradient based optimizers, it's linear, yeah. But I'm not that an expert in that particular case. But as far as I'm concerned, or as far as I know, optimization is bent to linear cases. Or if you have nonlinear something, then you have to make something quasi-static or something that you can make your linear static loads, right? Yeah.
Yeah, I guess it would come down to how to explain to the solver that the terms you wish to obtain comes from nonlinear, and then it could be like a plastic strain or whatever. It would be like extremely more complicated, right?
Yeah.
But that's
because you have your gradients, right? That's the
from
problem.
My perspective, I'm not losing the job yet.
No. There's definitely a lot of use for nonlinear analytics. That's for sure.
And do you feel guilty, like, your PhD moved the needle forward of developing topology optimization that will make in future every engineer jobless?
Oh, I don't think so. Well, as I said, that you can apply topology optimization, but a dumb engineer will always be a dumb engineer, and with topology optimization, he will be more dangerous, because if he makes a design and it's stupid, an intelligent engineer would recognize that. But if the engineer says, well, I did topology optimization and this is the optimized solution, and if one is dumb enough to just believe it, that's where the danger lies. So you always have to check it, and yeah.
It's surprising how similar FEA and topology optimization is in the general consensus, I guess.
Yeah.
Because I would say the same thing for FEA. It just makes everything more plausible in some sense. Like the stupid design looks so much smarter if you slap a rainbow on it, right? And then you see all those colors and mesh, and everybody's like, yeah, this looks like super, like awesome.
Yeah, and you trust the computer.
So I guess
that's a bad thing.
Yeah. So obviously, like, the knowledge and experience of engineer is always a limitation of every engineering tool out there. Like this, it's the same for topology optimization for FEA.
Sure, it's the greatest good.
Are there any other limitations people should be aware of when they use topology optimization? Because, like, we already know that you can just buy the software, right? Like, it's there on the market. It will most likely cost you, but you can have that, right? And then you sit down, you press few buttons. I mean, come on, like, the user interface is simple enough nowadays, so you can click stuff to make it happen, right? And in FEA, my answer would be, oh, you need to be really careful about nonlinear stuff like buckling, yielding, things like this, right? Because if you do only linear stuff, it's dangerous. So what is the pitfall of topology optimization? Because, like, you've made a PhD out of it, so I doubt it's just like, do 4 clicks and the outcomes pop, right? It's more complex than that. So what to pay attention to, I guess?
Well, definitely all the things you have in FEA also apply for topology optimization, because it's based on that. So meshing quality, something like your modeling, is the model accurate, is the forces accurate, and also very important is, are you certain about your loads? Because the solver is really straightforward, going to that point where the optimized design is for exactly that load case or that set of load cases. But if you change that slightly, angle off, amount of force slightly off, you could end up that it's a very unstable solution, like a ball sitting on top of a mountain, and you push it to the side and the performance gets worse drastically. So check for stable design, check for loading uncertainties, check for material uncertainties, all the stuff you have with your linear and non-linear, you will have to check with a topology optimized solution, because at the end you will have to do verification. Finite element method, check it. Yeah, this is one thing.
Oh, that's so cool. I wouldn't think about this one because like you're right. Like if you have like, and is there a tool that says I have this one force applied like this, but I want it to be like 5% off in all direction just in case? Like could this be automated somehow to make it more foolproof?
It could be. I've not looked into that myself, I must admit. I'm not aware of any tool in the Hyperworks environment where this is automatically done. But you can code it. So you can make a load case, and then you could change the direction and make several load cases, and weight them differently, and take the sum of everything to even the objective.
Okay. So could you do like, because I thought that topology optimization is done for one set of loads at a time. Could you do like more set of loads in like somehow? But how would that work then?
Yeah, the thing is, it comes from the formulation. So let's say you want to minimize the compliance, which is the equivalent to maximizing the stiffness of a part. Then you would have one load case, and the load case, there's the compliance calculated. Now the thing is, how to deal with multiple load cases. Let's say you have multiple load cases, and you then take the sum of the compliances of each load case, weight them maybe differently, and then you have the sum, and you're optimizing for the sum. So this is possible, but it influences the structure quite a bit.
How? Yeah, I can only imagine, but also like since you're running linear FEA, that might not be the worst case. But how much computing would last? Because like, if you would like, even with one load that you have like this, if you would move it around a bit, like this potentially can generate like, I don't know, 50 load cases, right? And then you need to combine them together, and like each run takes multiple times because like you remove stuff as you go and so on.
Well,
like,
it's not
this
linear.
would take ages to compute, or is it like, I guess.
Well, the thing is, it's implicit. So you have your stiffness matrix, and then additional load cases is not that much of a deal, but the deal comes with your iterations. So you don't have just to make this once, but for one topology optimization, it's depending on your structure and mesh grid and something like that. It's depending between 7 and maybe 100, 200 iterations, and one iteration consisting of doing one complete FEA of the structure. So it's rather...
But linear one, right?
Costly. Yeah, linear one. Yeah. But you could also...
So 100 iterations would be like... Okay, 2 hours maybe. Okay.
Yeah, so... But
like, I already have like a typical size of FEA problem I'm running. So I know more or less how much time I need to do 100 iterations of calculation. So that will like maybe 2 hours, maybe 4 hours, depending on the size, right?
Okay.
So that's...
But be aware of the memory requirement. Memory is pretty big. So even small models, you will have to do several gigs of RAM. So several dozen.
No, I have like several, like I have like 100 something in my computer.
Well, that's okay. I have models with a requirement of 250 gigs of RAM, but you can also then change it to an explicit. Well, it's not my computer, and I didn't have... Yeah, it was the university, so they had that. Yeah.
Yeah, we have the mainframe as well. I just learned that it takes you longer to drive to university, download the outcomes, and drive home to analyze them than to run the analysis on your slower computer.
That's the thing. Also, with home office at the time, internet speed is a big problem. I really drove to the office because I get the data faster than with the internet connection. Yeah,
that's so true. All right, like, could you show me how it is done? Like,
sure.
I'm curious because, like, I'm a geek, so.
Okay. I will introduce you to this example I have in my slide here. So this is density-based topology optimization. This is the load case of the C-clip. It's a pretty it's a pretty beginner tutorial, but it illustrates the things pretty good.
Like, it perfectly suits my level of understanding of topology. I'm sure.
Well, it's good to show it, I guess, but we will get also in more difficult, advanced elements or models. So basically, I will switch us off to just show a full slide.
Sure.
So for each and every element, you introduce a so-called density. So this density is scaling a lot of things, mainly the structural properties. In this case, it's changing the performance of the Young's module and also the volume. And so this, depending on the density being between 0 and 1, it's either a hole for density 0 or part of the structure for density 1. And so you have your fields to play around with. And you can calculate the mean compliance, calculate your restrictions, in this case a volume level restriction, where you say that you have this design space, so this whole elements, and you want to just use maybe 20-30% of it and place them wherever the solver wants it to, and this is the result. And I can show that to you.
But wouldn't the best approach would be to say, use the minimum possible? Is that, do you have to say because let's say that I would say I want to use 90% of the space. I can only guess that if I would say I want to use 70% of the space, the outcome would be different, right? Or would it be the same?
Well, no, it's not. It's definitely different. But this is the one formulation where you want to maximize your stiffness. The other one you are referring to is minimize the mass, so use as little elements as possible, but the restriction is the displacement constraint has to be met. It's also possible. We can do both ways.
Okay.
Yeah, so this is also possible.
One of those will suffice, I'm sure.
Okay. So I will switch over to Hyperworks to just show it to you. So this is a basic FEM model, right? So nothing special.
Okay.
You have your linear elements, linear loads. Nothing special. Material is steel.
Sure.
Properties P
so
shell.
I would guess that boundary conditions are important. Loading, as you said before, and so on, right?
So you can see it here. A little bit here is fixed in all 3 translational degrees of freedom. This is fixed in Y, and this is fixed in Z direction.
So you make it stable, simply put.
Yeah. So if you run this, simply run it. Yeah, that's basically possible. So this model can be run. But now the topology optimization is really not that complicated. So what you first need is your responses. So in this version 2021, it's under topology, you create a design variable. So this has to be there and refer the property where the design space is. So in this case, I will select this property. You can also exclude some areas from the optimization that, for example, all stuff around the loading points is there, cannot disappear.
Oh, so you can say something like, I want this to be attached by this way, and you cannot change it, but change the rest. Oh,
yes.
Okay.
That's pretty important. But we will skip that for here. And also you can see here the manufacturing constraints, like the minimum diameter, also the minimum diameter of the structural elements.
Oh, that's cool.
Symmetry, the way how material can get removed from which side, stuff like that.
So this is where magic happens, right? The topology magic, that you have those options to select.
Yeah. That's pretty cool, because it's done with filtering, and it's quite important to set this. But we will skip that for here, because it's also 2D examples, so it's not that important. So this is the first thing. The second thing is the responses. I was wrong there. As I said, the first thing is the responses, but yeah, here are the responses. This is mainly what we want to influence, so as an objective or a constraint. So in this case, we want to minimize the compliance, which is the same as maximizing the stiffness. So I select compliance here. Total compliance is okay. And I should name that, like, for example, compliance.
So you basically define what you want your structure to be like, right?
Yeah, what the objective later be. So responses is like stuff in a model which the solver can get. And this is one thing, compliance. And I do another one with the volume frag. This is the percentage of volume you get left at the optimization end.
Okay. So you're basically saying we are, like, if I'm wrong, just
yeah, sure.
Like we have this space, and I want it to be deformed maximally by 4 millimeters in whatever direction or whatever else the compliance was. And I also want you to check that if that's the case, how much volume I used before. And then you will use the volume as a measure of how cool the particular solution is, and it will run it a lot of times and select the best solution, so the smallest volume. Or like, am I understanding this correctly?
You're actually thinking a bit too complicated. It's just here the volume you have at disposal. So it's a PhD level of thinking.
Okay.
So this is like volume frac means the fraction of volume at the end divided by the volume at the initial. This is it. So if I don't have an exact value for that, but it will get clear in a minute. So I just created two responses, and those are appearing here: optimization responses, the compliance and volume frac. And now I want to create an objective and a constraint. With the constraint, it will get clear. Objective is straightforward. We want to minimize the compliance. The compliance is the inversion of the stiffness. So if I minimize the compliance, I maximize the stiffness. So this is this one. So I minimize. I will select the load step for this. I only have one. So this is straightforward. And now the constraint here, it becomes a little bit more clear. So this is about the response of the volume frac. And I will select here a upper bound of, for example, 0.3. And this is telling the solver that I want the solver to use at maximum 0.3, so 30% of all the elements for the final design.
Okay, and the goal is to be as stiff as you can with 30% of the volume, basically.
Yes.
Okay.
So imagine that every element would get a density assigned of 0.3. Then this would be fulfilled. But the design would be not stiff, because you know that you don't have any structures. It would be the same, but with with less thick. You could. So
imagine. But can you have something like, so the density doesn't have to be 0 or 1. It can be something in between as well?
It can be, yeah. It can range, but the solver wants it to be 0 or 1, because everything in between you cannot manufacture. You can manufacture holes, you can manufacture parts, but you can not manufacture some semi-value between. This might change with multi-material.
Okay, so basically, it would be something like a temporary information that this element is like needed, but not too much. So maybe in next iteration we'll remove it or something like that.
Yeah, we will see that in a minute. Because we can run through the iterations, and then we can see how the design evolves. So this is my initial settings, and now I will just run it. I hope I have defined everything correctly, but we will see about that. The thing is, this is a very easy example, and therefore the structure will not be that cool, stuff like that, but yeah.
Well, it's cool enough for me, to be honest, because I know from a fact that if you do a PhD around something, you think that it's mundane, but the reality of it is that it's actually pretty cool, I must say.
Yeah, I think so too. Well, this is running, and you can see here the iteration number counting up. So each iteration is a function call of the FEA, and now it's finished. Let's see, it converged.
So you basically did a lot of linear. Did a lot of linear FEA models in the background, and the topology thing decided we remove this, we remove that, we do this and that, and see.
That's basically it. And you can see here how the compliance went. So it decreased until this point.
Well, it's so smooth.
Yeah.
Like I was thinking that at the beginning it would be like, I'm guessing, and then it will be smooth.
No, it's gradient based. The solver knows in which direction to go. So now I can go into the results, and then you can see how the design forms. Pretty cool.
And can you animate it, like how the things disappear?
Yeah, sure.
Oh man, that's like so GIF worthy.
Yes. So this is the result window popping up. And here you have the different iterations. I will plot the element densities, and then we will animate it. So let's see.
So cool, man.
So this is the baseline design. So you can see here already in the legend that it's 0.3 for every element. Yes, this is the
Mhm.
beginning.
Yeah, that was the start, and now it starts to steal from elements and give to other elements,
Yes, right.
Because those who has will have more given to them.
Yeah, that's
Oh,
right.
that's so freaking awesome.
That's great, right? So you can see at the beginning where
Alright.
it really fastly removed all this section here. And then you can also see this, it's called checkerboard. It's a
But-
pretty bad thing. So because high density, low density next to each other, it's some numerical hurdle you get. And there are ways to get
okay.
over that, yeah. So this is
But
an example.
was there like a boundary condition where when the solver didn't use the elements on the left in the middle? I think it was pinned there, wasn't it?
It was
Like yeah, exactly where you
here.
had the cursor.
Yeah, you have to be.
And like
Yeah. Well, the thing is, you have to be sure about that those elements, as they seem they have disappeared, they did not disappear completely. They are still here, but with a very, very less stiffness. That's why you would have, if you make a reanalysis, you will also move the boundary conditions. So it's also a struggle I went with my PhD thesis. Yeah, this is definitely
yeah,
the
because
point.
otherwise you would if you'd manufacture this, you just missed the support you've defined.
Yeah, right. And that's now you can see why it's important to exclude some elements from the design space, especially where the loadings are and the constraints are. So you could also just create another component. So we'll do that and call it non-design. And we have to duplicate also the property because it references the property. There's no duplicate. I'll just make shell non-design. And we'll have the same material.
Oh, that's so cool, man.
I think the stiffness is also 1. Yes. And then the non-design would be not shells, but the non-design. So like this. And now we could
And you can basically like hand pick elements?
Yes. So you could, for example, take those elements. Let's see.
And could you pick some like one for me, just for giggles? We'll see what happens.
So which one you want to use?
Like something in the upper left corner, but not exactly in the corner. Like how? Yeah, this one. That's awesome.
That's one?
There was nothing there before. I think. Yeah, I think that there was nothing there before. So we will see how it morphs around to make it happen, right? Because it will be somewhere there.
Yes. Yeah. All right. So I moved that to non-design. And it's a little bit awkward because the color is the same. You cannot really differentiate between them. So those are now non-design, right? Okay, now I will just run the simulation once again. Let's make here a 2.
This is freaking fantastic.
Yeah, you like that? Yeah, it's pretty cool. Because
it's like so much fun, right?
Yeah.
Like I could imagine working in a field doing this, it's more like I guess that if you do like car parts or plane parts design, this would come in handy, right? In like typical civil engineering, I think it doesn't have a field to it, I guess. Maybe in some cases I'm unaware of, but like in like manufacturing parts, like plastic parts or like metal parts for machines or stuff, this is so freaking awesome. Like I would love to do the animations, man. It's so cool.
So this is the model. I think it's finished already. Now let's see.
Oh wait, but it's not connected. That's
cheating. That's really cheating. Yeah. Well, what's the hurdle here?
It would be like more.
Yeah, it should be, right? What's the hurdle here? I guess is that I gave him too less material to use.
Okay.
So what you can see here is that it has the density of 1, but it's not connected to the structure here. So basically it's telling me that this structure, there's enough loads, maybe because it's balanced, exactly balanced, right? maybe if I include the force at the upper one a little bit, then you have an asymmetry, and because if you perfectly sum it up, you have no rotation, right? But let's see about that.
Yeah.
Because we can change that, right? So I will change the
sure.
upper force, maybe 10 newtons more, right? And then,
by the way, it's exactly like in FEA. If you have like a perfect balance or perfect symmetry in a model, it's always the worst type you can do. Like,
yeah.
It's so much easier to do stuff when they are not ideal.
Right. So I changed the upper load by 10%. So this is now 110.
Like you can add more material too if you think it will help. Like it's
well,
like,
we will do
I don't
both.
care how optimal the design is.
We will see. We will do both. It's so quick, so it's not a
precisely. It's like, it's so cool because like someone will see this like, hey, he did it in 10 seconds, and then you get like industrial grade problem, and it computes for 5 hours, and you're like, oh man, that was like cheating.
Yeah, that's definitely the thing. There's some different algorithms who can do that faster on that. There's even apps on the Android or iPhone which you can do a topology optimization. It's called TopOpt. And there it's in seconds. You just put loads and boundary condition, and it's really fastly converges.
Oh, that's so cool. I need to download that. I will show my kids what I did at work today.
I think you'll love it, yeah.
I've seen a one that has like an FEA solver that I don't remember the name sadly, but you could like move with your thumb a structure, and it calculated how it acts as if your thumb was enforcing deformation. That was so incredible.
So now you can see a little bit, but the structure here it will not get. Maybe the mesh is too coarse.
Yeah, maybe
also too less material. Well, what I can do, we can just split each element once, and then we can have a little bit of a finer.
You can add few if you think that it will help. I'm okay with that.
Let's see if that works. Plate elements. That should be. I split the plate elements. Now we're talking, right? A little bit more, and also I'm also doing the response.
You could do like if you start your own company, you can have a plate. Select that the logo of your company cannot disappear. Make a smart like thing, and then it would animate into the logo of your company. That would be so awesome.
That would be great. Yeah, you could definitely do that.
It's topology optimization in marketing. Like this, like it's another PhD dissertation easily.
Easy. That's for sure. Yeah. Well, that pretty much the PhD thesis about advancing the topic, also adding nonlinearity. Good friend of mine is also working in that field, and so.
Yeah, adding a nonlinearity would be awesome, but it would take so much more computing. Even in a case like this, like you can see that even if you like increase the mesh, it's like 4 times more elements. We could actually see this calculate. It wasn't like a zoom ready. You had to wait for it, right?
Yeah, right.
So we are at the point where adding more elements will actually take time. So clearly it is time consuming.
I just changed the limit number of of iterations. Sorry, it's about it just stopped because of the limits of iterations. And we'll do that again.
Happens all the time in happens all the time in FEA. So it's like it's a normal thing. Also, this is good thing to know. Look, folks, how complex this is, right? It's a relatively simple example. I selected a stupid element in one place.
Yes.
Right. And now it's like, okay, let's do stuff. In FEA, it's exactly the same. Everything looks so simple until you sit on it, and then you have to like do stuff, and it's so much more difficult then.
So now I'm pretty excited about what this is converting to. So I'm reloading
I
the
hate
model.
doing live presentations. Like that's for sure. I rather have that on slides because then you know the outcome.
Then you're sure.
Sorry for putting you on a spot. Maybe.
Where's the fun in that?
Oh, that's so nice, man. Like I really like with the bigger resolution. It looks so awesome.
So I will just make
Oh,
a
you
filtering
have the
here.
average. Yeah, it's the average, non-average outcomes, of course. Yeah.
So you can see it's connecting here.
Because it was like rotating one way, so it kind of like threw a leg there to counter it. That's cool.
Yeah. So if you increase the force here even more, the thing is why this is not connecting is because there's no load path to it. If you include here a small load, it will definitely add that.
Oh yeah,
but it's not just floating in space. Yeah,
because it could, because there are no, like, you see, this is what gets a perfectly stupid question, which also proves that there are stupid questions. And I just asked one, and yeah, because if you would like add a load, it would have to go to the support, right? And I just threw like, let's do this and see what happens. And
sure.
It so happens that if you don't have that's so cool, man.
But you can add a small load, and then you will see that it's attaching that to the whole structure. Let me see, that's on the analysis.
Oh, add a big load. I want my element to be loaded properly.
Okay, now then let's do 500 newtons, for example. So the base model is with 100 newtons, so the main force will be that one in the top. And then I will just create a load here. Let me just check.
By the way, does it have problems with, because you, as I see, you apply loads in the nodes.
Yes.
So, people who do FEA would cringe seeing that, because it's like a singularity thing and so on. I guess that this can filter this out somehow, right?
Sure, you can use RB3 elements for that purpose. That's not a very...
Yeah. Let's not go there. It's
So, which direction you want the load to be in?
I don't care, like, pick one.
Okay, then I will do
it's my point, so I'm like
upwards.
I already have my thing in a model.
Okay.
Okay.
All right, so this is that, and then just run it again. Maybe this time is number 3, that we can see what's the difference between that one and the one last. Yeah, and then we can get the difference.
Oh, this is exciting, man.
Mm-hmm.
But the graphical, like how this evolves, it's so intense. That's crazy.
Pretty big stuff, yeah. Also, I'm in the phase of learning the new layout. So this is Hyperworks 2021, and this is the old one, right? So this Hyperview, this looked more like that. So the traditional Hyperworks until 2019, and this one is the new layout. And you can also do post-processing here, but not that advanced right now, I guess. So I like the old way a little bit better, because screenshot
I think that they will introduce the new layout to FEMAP at some point as well, and like this would make me afraid, I guess.
Well,
because,
for sure.
Like, when you get used to something, it's so difficult to switch.
Well, the thing is, you get that ribbon layout for pretty much everything, so that's definitely coming.
I'm not a big fan though. Like somehow I got used to, like in Word, in Excel, I got used to it. But like in FEMAP, I hope they won't do it. But like it's unavoidable, I guess. It's such an industry standard at this point.
Yeah. I think so too. But at the beginning, I was also not very, very happy about the new layout. But right now, I'm in the process of accepting it. And also there's some kind of cool new features. So, all right, now let's see. Here you go.
I guess that... Oh, yes!
Yes!
My point is included.
And you see also that the structure
and could you animate
thicker.
it? Could you...
Yeah, sure.
Yeah, because of the law. That's so freaking awesome. Wow, that's... Oh, man, that's so cool.
That's beautiful, right? You can also see on the left, at the beginning it had the link, but then it all somehow capped it. Right?
It decided that it's self-sufficient in some sense, so it doesn't need it.
Yeah, that's right.
Oh man, that's wonderful. That's so cool. Like I guess this is the same thing with nonlinear FEA outcomes. If you animate like a decent analysis in a decent way, I could just sit and watch it and just relax by watching it. So.
Yeah, so should put some FEA meditations out there. Maybe there's a market for that. like turning stuff.
You feel like a quad 8 element. Take a deep breath.
Yeah, that would be awesome, right?
And then like those stroboscopic things running from start to back, right?
You feel the tension
Yeah, I
go
see this
away.
happening. Yeah.
Yeah.
But man, that's fantastic.
Yes.
Did you happen to do like bigger, like I know that we want to do a bigger example because of the computing that it would require, but maybe you have like bigger examples done that you could show? Because like, this looks fabulous to me because I kind of like, I think I know what's involved, and that's magic, right?
Yeah.
But if you have like a bigger one, it would look even better.
Well, the thing is, I think not here at that PC, but what I can show you is the slides. Maybe.
Okay, awesome. If you have slides, that
look
would be
into
marvelous.
it. Let's see. I think I got something here. Yeah. See that? Here we changed. This was a multicopter stage, and we changed the positions of the rotors and also of the batteries. And by just changing them, you get different strategies, different structures, and also different performances regarding, for example, your the translation is so bad. Medium indulgence. I think this should be compliance. And volume is correct, and focus, I think this is the point of center of gravity. And yeah, because if you have a multicopter, you care a lot about stability and center of gravity, and then you can do different topology optimizations, and you can see, all right, those designs are with a lower center of gravity, and that's better.
Yeah. I really like it. So basically now you could 3D print the whole thing, and you could also like how long did one compute when you say like let's
this
test
one was bigger.
This rotation?
I think 1.5 days, but on not a very decent machine, something like that. This one was the one with 100 plus gigs of RAM. Yeah.
Okay. So this takes like a bit longer than one run of nonlinear FEA, unless you had like a lot of load cases there.
Yeah.
And you included all of them at once.
Yeah. It takes a while.
Okay. So that but it's so wonderful, man. Like that's freaking awesome.
Well, I like the field also a lot. Yeah, it's pretty cool. Yeah.
Yeah. That's so neat. Like, do you have anything else?
Well, let's see if I have something in here, but well, this is the cantilever beam. So simple.
Okay.
This one. So 3D structure, and you can see the elements. So it's not that big of a model. This will take maybe a half an hour, a quarter an hour, something like that.
Okay.
On a desktop computer, and
but you could also do something like,
yes, cross structures.
Yeah, exactly. So could you? That's what if you would go back to the because that goes to the civil engineering, I guess. Here, like, could you design those? Yeah, you have like automated reconstruction. Oh, okay. So you didn't define the lines we talked before, but what you did is like you did some sort of 3D shape, and then like you.
Well, the thing is, you have your topology optimization here, the result of it, and you want to cut it into straight parts, but you don't have any idea where the straight parts are. And the one center point of my PhD thesis is you use the stress directions to just put it into different categories. And this is a little bit with you get your principal stresses and the directions from that. Get the absolute biggest one. Get the direction from that, and each element you get a direction, and you search for the points where the maximums are. Well, it's a little bit complicated, but if you want to see that in the C-clip example here, you can see that you have this pressure ring, this outer pressure ring of the C-clip. Well, and then you can see the stress directions. If you do that on a polar diagram, you can also do just a histogram of it, and you see the directions and then assign it to the elements, and you can easily get your points straight. And then you have this one, so it's a clustered result. Yeah. Then you just have to do.
And then you say shape. Each one of like one type gets one beam, right?
Right. Yeah, one beam, and then you just have to do the intersections. And this is then done with CAD geometry, so programming CAD geometry, how you do your welder tubes, which cuts which, and stuff like that.
Awesome. Those are empty inside, right?
Those are MTO. Yeah.
And does it like take into account the stability of it?
No, it
Or
does
no, it's
not.
just linear
It's
stuff,
just
right?
it's just linear, right? Yeah. So
Ah,
buckling would
okay.
be definitely the point from this
Awesome.
cantilever
Well,
beam.
in that case, like maybe I'll do the analysis of it, and we'll see what the difference is. Like, is the
Yeah,
outcome
sure.
like typical? By this I mean, like, let's say you have a cantilever like this, right? You
Yes.
load it with a load that you know. So basically, what we see here is the topology optimization answer to the question: what would be sufficient?
Yes. Yes.
So
What
basically,
would be
for
optimal?
instance. Of course. So basically, the idea would be that it's possible to have an optimal topology optimization solution that is actually wrong because it doesn't take buckling into account, for instance.
Well, yeah, it does not take that into account, and the cantilever beam did not show any pipes, right, or tubes. So it's just full material, but we had the design change that we want to use pipes or tubes. And therefore,
okay,
you have different things, but you would never consider buckling of pipes, tubes in a topology optimization. Because, yeah.
Okay.
Calculation time.
So that's cool. Like I can do that, and we will
Yeah,
see
that would be a great
if
great
the
thing.
outcomes is actually like manageable. Because that's curious for me too. Like how accurate you can get. Like I'm not sure how thick those are, but like I have a PhD in shell stability. So dude, that's my place.
All right. Next time I will come to your channel.
I can check that and be so exactly like
talk about your
I will come to you and
you.
I'll be so smart and so like we can do that, and I will join your channel and say like, look, this topology optimization Manuel is always talking about, like, this is kids, this is not how it's done. That would be so funny. I like, because like it's such a complex thing, right? And then you have like those shallow empty shells like crossing through each other. It would be so simple to make something wrong this way. So so that would be one of the dangers of topology optimization. Like it looks so smart, it looks super automatic and stuff, and then that's something we definitely have to do in the future, man. Like,
great, let's do that in the future. Looking forward to that.
So man, thanks for letting me know all of those things. Like
sure.
I'm fascinated. Like I love engineering in general. So so like the complexity of it all never stops to amaze me. Like even the simple plate, it was so incredible to see how it like merges and develops into a shape, right?
I like that too,
as an engineer, I could draw on a paper, like, I think that if the force is this way, I want this element, that element. Like I would kind of like, in a simple case, I wouldn't nail it perfectly, but at least I had a decent chance of making something that would work more or less, right?
And that's the best approach, I guess. Do your things first, and then do your topology optimization, and then have a look at it, a critical. That's the way it's supposed to do.
This is how I do FEA as well. If you don't know what the outcomes should look like, maybe you shouldn't even start, right? It's like, I actually once managed to convince myself about the wrong outcome. I forgot to include some critically important loads in the model. Like, it was a misclick of some sort. Like I thought that I applied the load and it was not there. I didn't verify this. So I ran the analysis. I look at the outcomes. It took me 2 hours to figure out a completely plausible way why the model behaves so weirdly. Having a PhD really helps in those things. And then a colleague, because we always verify reports, said like, dude, you didn't apply load. And I was like, I had such a wonderful theory why this could work.
Always check your model.
So I guess that's the same.
Yeah. That's the thing you have to consider.
But that's so cool, Manuel. So thank you for all the information. Like it seems that this is a super cool field. Like, would you recommend people to go into topology optimization as a career choice, let's say?
Well, I don't think it's completely just a career choice, but also just to get the benefits of this field. It definitely helps. So if you're a good structural engineer, you become an even better one if you have those tools at hand. And you can also learn a lot of structural behavior. So you look at a lot of topology optimization models, and you can identify certain criteria, some certain rules. Put, for example, material to the outside to create more inertia. stuff like that, you will see that and also deduct from it. So it's definitely a good thing to do.
Okay.
Yeah.
That's so cool. It's amazing how similar it is to nonlinear FEA. Because like if you do nonlinear FEA, you learn stuff, how it works. Like
yeah, sure, yeah.
And it's like even if you stop doing FEA in itself, the knowledge and the understanding of stuff remains, right?
Yes,
That's so awesome. So at the very end, could you tell us where people can find you online? Because I know that you have a YouTube channel where you talk about a lot. So I'm sure that people will be interested
my YouTube
in learning
channel,
more.
I think that's the main point. Yeah, you find me on YouTube under my name, and I think we will just link the YouTube channel in the description.
I will post a link below the video, so you can go to Manuel's YouTube
I'm doing
channel.
a lot of topology optimization.
It's like since
you want to do that, come over,
and
have a talk.
Since you already defended the thesis, that would be Dr. Engineer Manuel Ramsaier.
Oh yeah.
Yeah. That's so cool. Man.
Yeah,
it's like it's good. It's good for algorithm, though. I heard that if you have like credentials in a field you talk about, it actually helps you to spread them.
I think so. Yeah,
that's a smart move. I haven't done it yet. So
well, all the people assume that you have expert knowledge, but it's still to prove that.
Yeah, when you do PhD, you never look at it the same way.
No. You're still the same person, and you still make failures, and have to be careful, and always be open to learn something new every day. That remains. Yeah.
I think that what it gives is more or less the feeling that while people may have expertise in many fields, it doesn't make them like godlike in any sense.
No,
you just know a lot of stuff, a lot of things about a certain topic,
one piece,
but that's like right. More or less, as profound.
And you
as
endured
it.
That's always a thing.
Oh yeah, like that there's a story there, and I will get to you later, man, about your PhD stories. I think that people will really enjoy if we share ours, like
sure.
PhD stories. Like if you have kids and they were like not behaving very well, you can send them to the session of PhD stories, and we can tell how people can be treated and they will behave like angels from there on. Doesn't work on my kids though, so I don't know.
just have to keep trying.
We don't give guarantees though.
Right.
All right. So Manuel, thank you so much for coming.
It was really a pleasure. Yeah. Same for me. It was really a pleasure talking to you.
Yeah. Okay. So have a wonderful day, folks. Yeah. And also, if you have any questions, you can like write them down below, and I make sure that Manuel will come from time to time to take a look. And
I will have a look.
Yeah. I'm sure he'll be more than happy to.
Definitely.
All right. So see you around, guys.
Bye-bye.